The solutions to the quiz are posted on your homework. There are a couple of different scores. One of them is for an effort grade on the homework itself, and the other two are for the challenge problem in one of the group quizzes. And the other group quiz, of course, was turned in the same day online. Okay, and so that was out of a possible of 11. 5 and 3 is 8, and 3 is 11. So each one of those was worth 3. Again, the solutions to the quiz are on your website, on the home page, and I'll have the solutions to the other two, I'll pass those out on Tuesday. There's also the question of that problem that involved two waves that were moving relative to each other, and we're looking at the simple harmonic motion, and I'll also go over that one for you on Tuesday. So our next quiz then is next Thursday. That'll be on the compression waves from chapter 17 for the most part, and chapters 33 and 34, which is our introduction to light. Then we'll have a midterm 2 weeks from today, and that'll be on all of these sections. So there are a couple of subjects that I still want to finish up from chapter 17, and so I'll start class with that, but then I'll jump right into chapter 33. The reason we're making such a big jump in the chapters is that chapter 33 is when we start dealing with the properties of light waves. And so in order to understand light waves fully, you have to go through all of the principles of electricity and magnetism. But I'm going to skip over that for the moment and just look at the basic properties of an electromagnetic wave without you needing to fully understand what an electric or magnetic field are. So I think that fits in more naturally with what we've already covered with wave motion by just thinking of it as being a different kind of wave. And so that's the reason for doing things that way and jumping straight from 17 to chapter 33. Okay, and so are there any questions about anything?
Can we talk to you about the grade after class?
Yeah, or during the lab is a good time. But after class today usually works out okay because we're going to have an in-class activity, and so I have an office hour that goes for another half hour following.
So next week's quiz is about those chapters?
Yeah.
And midterm is about the same?
Everything.
Oh, everything.
Yeah. So midterm is everything that we've covered so far. Any other questions? Yeah.
For the labs, I know like the in-person lab last week, we got a physical paper. Is that part one that we're turning in next week? Or are we
You're turning in the virtual and the in-class part together as a double lab assignment. And so that's due either a week from today or a week from tomorrow. And I'd rather you just give it to me as a hard copy because it's a little nebulous as to whether you would upload it as lab 1 or lab 2. And so I don't want to get a bunch of scattered things that, or some is lab 1, some is lab 2, and then some I'm getting as a combination of them. So it's easier for this first two to just take it as a hard copy that you would turn in lab next week. And that'd be the only one where you turn it in as a hard copy.
And the hard copy is going to be the one from what was the
Everything.
last week and
Both. Yeah. Question?
So the packet that we have already, is that the virtual component in there too in that packet? Or is that only the physical part when you print out the virtual part?
The virtual part, I don't know if you got my announcement, but I spelled that all out. I also wrote it up on the board.
Okay.
That was part 2, I believe, from lab 1, and parts 1, 2, and 3 from lab 2.
Okay.
But that's all been written down, and so if you're not sure, check with me, but it's basically just everything that's a simulation from the first two labs. Any other questions? Yeah.
Apologies, what is next week's quiz going to be on again? 7:33, yeah, 34.
Any other questions? Okay, so a couple of things from last time. We derived this expression for the Doppler effect. Remember that we used the top sign for relative motion toward and the bottom sign for relative motion away. And so I just wanted to look at one more example of that, which, at the end of class last time, we looked at a case where we had a moving source and a moving observer. And so if we have that kind of a situation, then that could also be applied to ultrasound. And so I wanted to just look at an ultrasound application of this, because that's kind of a fun one. And it's a little bit of a twist on what we've learned so far. Here is an ultrasound picture of blood flow. So there's a picture of blood flow that is coming from an ultrasound. And so let's say that the blood is moving. So we'll call this velocity velocity of the blood. And then we have a source here of sound, ultrasound. Which produces waves that have the velocity of sound. And, or I'll just call that V here, where V is what I was calling before the velocity of sound. So what will happen then with an ultrasound is that the waves come in and they hit this is essentially the receiver for the source radiation. And so what we get from this first interaction then is an F0 prime, if we were to call it that, that's equal to F naught times V sound plus V blood divided by V. Okay, because in this case, the blood is moving toward the source of the sound, and so you have a velocity change, but the source is motionless. But then in the second part, after reflection, then what we get is a moving source, because now the reflection of the sound is moving. And so in the amount of time it takes for a wave to hit the blood, the blood has moved a certain distance. And so that's shortened the wavelength if it's coming toward the ultrasound. And so after reflection, F naught double prime is equal to F naught prime times, and so in this case this is a moving source. So this is the velocity of sound divided by the velocity of sound, and then it's moving towards, so that'd be minus the velocity of the blood. And so if we put these two together, basically, in other words, if we take F naught prime here, and we replace it with this, and we multiply them, the V's cancel, and so what we get then is that F naught double prime, which is the frequency that of the received waves, is equal to F naught times V plus V blood divided by V minus V blood, where this is the velocity of sound. So essentially, it's this equation where in the first part, it is the observer. You can think of the blood as being the observer. It's getting a certain frequency from the source as it's moving toward the source. But then after the reflection, what you get is that frequency, which came from the blood, is now the moving source. And so we use that equation for the reflected, which is what comes back to the ultrasound. So it ends up being a combination of V plus V blood divided by V minus V blood. And so that's what you get then when that's the frequency shift that you're looking for when the ultrasound picks up an anomalous shift in the velocity here. And so that anomalous shift in the velocity then is associated with the blood, in this case moving toward you. And so that is also in a similar way, although not exactly the same, with the police radar gun. Because the police radar gun comes in and strikes the car. And so initially then, it's the car that's getting a Doppler shifted frequency from the source, which is the police radar gun. But then after reflection, it's the car that's the source. And so it's a moving source, and then it's a fixed observer. And so when you put those two together, and if you just take this expression for F naught prime and plug it in there, you see the V's cancel. And so this is what you get. Okay? And so it's a similar kind of thing with electromagnetic waves, but a little different just because of the fact that electromagnetic waves always have the same velocity. And so it has to be done a little bit differently. And when we get to Physics 2.8c, I'll go into more detail with that. Are there any questions about how this works for ultrasound? How this is a combination, basically, of the two motions together. That was kind of an interesting application because we all see ultrasound all over the place. Okay, next thing I wanted to look at is shock waves. And this is the last subject that I'll be covering from chapter 17. So shock waves then occur when the velocity of the source exceeds the velocity of wave transport through the medium. So what we've already seen is that if you have a moving source that squeezes up the waves on the inside in the direction of motion, so this wavelength is small, this wavelength over here much bigger. Lambda 1 for the shorter wavelength, lambda 2 for the bigger wavelength. And the reason for that is that you're moving away from these waves, and so in the amount of time that it takes you to produce one complete cycle, you've also moved that extra distance. So here's your complete cycle. That if you've moved this extra distance in this direction while you produce that complete cycle, you're moving away, then you've got an expanded wavelength. So this is when the source is stationary. It's going to produce a wave that looks like that. When it's moving away from the direction of wave motion, then it stretches the wave out, because in this amount of time it's moved by a distance, velocity of the source, times the period of the wave. So that's how much the wavelength has been expanded by, is the velocity of the source times the period of that wave. But when it's moving toward, like this, then it moves the velocity of the source times the period of the wave in the same direction as the direction of wave energy. And so that shrinks the wavelength. And so this is your lambda 1. And this is your lambda 2. In that picture. Okay, so it squeezes more and more until finally you reach a limit. And in that limit, now the waves can't get away because you're traveling at the velocity of the medium. So that's what happens here. This is what produces, for example, a sonic boom. Okay, and so when the velocity of the source is greater than the wave velocity, then the waves try to get away, but the wavelength is dropped to 0, and then basically, as you go to faster and faster speeds, you're just carrying more of this compressed air along with you. It's almost as if the airplane was heavier because of the fact that it has to push through and carry along with it this extra compressed air. Okay, and so that's what creates the sonic boom. This is what we call the shock wave from the sonic boom. Okay, and so this distance that you travel here would be the velocity of the source times the time. And this distance that the wave would travel out in this direction would be the velocity of sound times the time. So you can work those two out, and you can get that the sine of theta is the velocity of sound divided by the velocity of the source. And of course, this isn't going to work if the source velocity is less than the velocity of sound, because then you get a sine function that's greater than 1. Okay? And so that works out nicely because you certainly don't expect that to happen. And so if you get those two mixed up, you know, if your calculator says error or a little bit of smoke starts coming off of it because you said 1.1 inverse sine, then that's telling you that you got the two mixed up. Okay, and so this is the source, the sound source velocity. Okay, and so that means that this angle theta that we can measure here that's associated with the shock wave front, this theta is equal to the inverse sine of the velocity of sound divided by the velocity of the source. And so let's say, for example, now, when jet planes were first trying to break the sound barrier, there was a big problem. Chuck Yeager was the first one to break the sound barrier. And a lot of people had tried before he did it. And they were unsuccessful because they felt like their plane was shaking apart. And so essentially what's happening is when it got close to the sound barrier, certain parts of the plane were experiencing huge pressure differences. And those pressure differences generated forces, which made the plane feel like it was going to fly apart. And so they were starting to say, well, if God had meant you to fly faster than the speed of light, he would have given you wings and the ability to fly or something. But he just pushed through it. And so all of that vibration and stuff settled down once he got going a little faster than the speed of sound. Then he was just carrying this air pocket along with him. So if you're looking up at a plane, and the shock wave front looks like this, you look straight up, you see the plane but you don't hear a thing. I guess it hasn't broken the sound barrier yet, is what you might say. Not realizing that that's not exactly what's happening. And then, when the plane gets to this point, it's a little ahead of you, then finally you hear that loud cracking sound. That loud cracking sound is that shock wave front finally hitting your ear. But not when it's straight above you, it's when that shock wave front hits your ear that you get this big variation in pressure between atmospheric pressure and the pressure that's being carried along with the plane. Okay, and so then somebody else standing down here then is looking up, going, oh, that plane hasn't broken the sound barrier. I don't hear a thing. And then gets over to here and goes, oh, that plane just broke the sound barrier. I just heard the crack. That's a misconception to think that way, because it's always continuously breaking the sound barrier and carrying along this shock wave pattern with it. And so the faster you go, that changes the shape of this, and it also increases the amount of pressure that you're carrying along with you. Okay, and so it creates a louder boom. And sometimes with when the space shuttle was still in operation, you would hear two booms when it would come in toward Vandenberg Air Force Base. One boom, I always thought maybe one was a reflection off a mountain or something, but one boom was coming from the wings, and the other boom was coming from the tail. So you're getting two different booms that you were hearing, and that thing was going something like Mach 8 or something. I don't know, when it was coming in for a landing. I mean, it was going really fast, and then it had to slow down. And so if you were going to Mach 2, what that would mean is twice the speed of sound. The speed of sound is 340 meters per second, then that would be 680, right? Or if you're thinking about it in terms of miles per hour, something like 700 miles per hour versus 1,400 miles per hour. Same thing. And so for that, then you could say that the sine of theta would be equal to v divided by 2v, because the velocity of the source would be twice the speed of sound. And that would give you the sine of 1/2. Sine of theta is 1/2. Or that would give you theta is equal to the inverse sine of 1/2, which is pi over 6, or 30 degrees. And so that would tell you then what this shock wave angle is. And so the total angle then would be 60, but measured from the center of the plane up to the top of the shock wave, it would be 30 degrees. Any questions about that? You know, there are lots of different examples of shock waves in nature. Turns out that when our solar system first formed, shock waves from a supernova blast, it's believed, are what caused the solar system to collapse and become the sun and the different planets. And so you would get, now supernova explosions are incredibly violent. If our sun were to go supernova, and it can't because it's not heavy enough to do that, but if it could, and it could produce the amount of intensity and energy that a supernova would produce, the Earth not only wouldn't be there anymore, it would be completely vaporized. That would be it. It would be completely gone. If you had, say, 4 light years away from a supernova, and here's the Earth, you wouldn't know about it for 4 years. But then when it hit you, it would blow off a good portion of the Earth's atmosphere. So it's thought that we've dodged a lot of bullets in the history of the Earth over 4.6 billion years, And when you do the math, it looks like we're not going to survive one of these things if the supernova is within about 65 light years of us. And so, been kind of lucky then to have survived. But there's also evidence that the radiation from supernova explosions that are farther away from that may have helped to get amino acids forming. And also just the, I think it's the right-handed form of the amino acids, because mu mesons tend to produce mutations in the double helix molecule that, that favor right-handed molecules over left-handed molecules. And so if you take the same chemical composition of life, but you make all of the molecules left-handed, it's not going to work. Life has adapted to these right-handed molecules, which is an indication that it was probably the added mutation rate that was caused by these cosmic explosions that favored the development of life out of right-handed molecules versus left-handed molecules. And so that's a theory that that's one pretty good way to explain it, just by knowing the mu mesons favor the production of right-handed molecules, and those mu mesons are part of the energy that's released from a supernova explosion. When you crack a whip, the end of the whip is moving faster than the speed of sound momentarily, and that's what allows you to hear that loud snapping sound. And so there are lots of different examples of shock waves, and I think it's safe to say we wouldn't be here if it weren't for shock waves. Okay, so let's leave this subject now and move ahead to light. I've got a handout for you here, which hopefully is legible enough for you to read, but it's going to go over a lot of the... Oh, there was one other thing.